Hey everybody, welcome back to Math 251. In this video, we are going to be talking about L'Hopital's rule, which is a very special rule that we can use when we are taking limits of functions. We have two flavors of this rule that we will be talking about in this class. So let's look at the first one right here. Basically, if we have two functions that are differentiable over some open interval that contains the point that we care about, and if both of the limits as x approaches this point that we care about of our two functions f and g are both equal to 0, then what we can do is we can just take the derivative of the top and taking the derivative of the bottom. Now we have to be careful here because this is not the same thing as using the quotient rule here. What we are doing is we are taking the derivative of the top and taking the derivative of the bottom, but this is not the quotient rule. So this can occur when we have the limit as x goes to a of our top function and the limit as x goes to a of our bottom function are both equal to 0. Assuming, of course, that both of these limits exist if we take the limit of the quotient here. And we also have that this result holds if we are considering one-sided limits, of course. That also holds. So this is the first flavor, when the top and the bottom are both equal to 0. We also have another one where I still have these two functions, f and g, and I'm taking the quotient of them. If I have that the limit as x approaches a of my top function and my bottom function are both equal to positive or negative infinity, then I can again take the derivative of the top and the bottom. Again, this is not the quotient rule. We are just taking the derivative of the top and the bottom. If you want to see why this works, there's a nice proof in the textbook, but it is pretty mathy. So we'll just, take our word for it here, and it's a pretty cool rule. So also the thing with L'Hopital's rule is if we need to keep taking derivatives until we finally have an answer, then that's okay. We can use L'Hopital's rule over and over again on the same pair of functions until we get an answer. So let's try L'Hopital's rule. We want to evaluate the limit as x goes to 0 of e to the x minus 1 divided by x squared. So the first thing we need to do is check to see that L'Hopital's rule holds in this case. So if will call f of x my top function, that's e to the x minus 1. So if I take the limit as x approaches 0 of e to the x minus 1, well, let's see, e to the 0 minus 1. E to the 0 is 1, so I get 1 minus 1, which is equal to 0. So the limit as x goes to 0 of the top function is 0. If I look at this bottom function, the limit as x goes to 0 of x squared, well, of course, this is also 0. So this falls under the first category. As I take the limit as x goes to 0, the top and the bottom are both equal to 0. So what L'Hopital's rule means is that I can take the derivative of the top and take the derivative of the bottom. And I can do this until we get an answer. So I have that my limit here, the limit as x goes to 0 of e to the x minus 1 divided by x squared. If I take the derivative of this, I get the limit as x goes to 0. Well, the derivative of e to the x is just e to the x, and then I have minus 1 divided by 2x. All right, so let's check this out again. If I plug in x equals 0 into the top, I still get e to the 0 minus 1, which is 1 minus 1, or 0. If I plug in x equals 0 to the bottom, I still get 0 on the bottom as well. So at this point, we still have 0 over 0. So what I'm going to do is I'm going to take the derivative again. So this is equal to the limit as x approaches 0 of e to the x divided by 2. Okay, well now if I plug in x equals 0, on the top I get 1, and on the bottom I get 2, which is our constant, right? So our answer here is 1/2. So what we have just decided is that our original limit, this guy right here, the answer to this is equal to 1/2. We have to be careful to make sure that we are writing our limits each time, because this function is not the same thing as this function is not the same thing as this function. We're not saying that the functions are equivalent, we are just saying that the limits of the functions are equivalent as x approaches 0. So in this case, we have to take the derivative of our functions twice, which is totally fine. We can do it as many times as we need to. We also have to be careful to make sure that we actually have either 0 over 0 or infinity over infinity. If we had, for example, like 0 over infinity or infinity over 0, we can't apply L'Hopital's rule. It has to be one of those two flavors. So let's take a look at another example. We have the limit as x goes to infinity of 4x cubed minus 6x squared plus 1 divided by 2x cubed minus 10x plus 3. So if I plug in, quote, plug in infinity into the top and the bottom here, I would get infinity over infinity, which is our second case here. So let's take some derivatives and see what happens. So the limit as x goes to infinity of 4x cubed minus 6x squared plus 1 divided by 2x cubed minus 10x plus 3. If I take the derivative of the top, I get the limit as x goes to infinity. The derivative of the top would be 12x squared minus 12x. The derivative of the bottom would be 6x squared minus 10x, just 10. Well, if I were to plug in infinity again, I still get infinity over infinity. So let's take another derivative. The limit as x goes to infinity. This time I get 24x divided by 12x. If I plug in that x equals infinity, I still get infinity over infinity. So let's take one more derivative. This is the limit as x goes to infinity of 24 divided by 12. And this finally gives us a constant of 2. So this means that our original limit, the limit as x approaches infinity, of 4x cubed minus 6x plus 1 divided by 2x cubed minus 10x plus 3. This original limit is equal to 2. So this is L'Hopital's rule in a nutshell. Hope you learned something, and I'll see you later.